So we are on to parameter estimation. So of course we have an unknown parameter or maybe a set of parameters. Both we will, both case we will deal with it. Or later we will also look at multi-parameter estimation. Of course, we are estimating because they are all unknown. Of course, if there is a known, there is nothing to estimate, right? So they are all simultaneously unknown. So let's deal with one unknown at a time, right? So we'll deal with the single one. And here itself there are two cases. One is the parameters are random variables, and this is non-random. So non-random means they are unknown constants, whereas when we say random variable means the theta has some density function, right? It has some density function, right? That's what we mean by random parameter. So today I will do random parameters, and then so this is relatively easy to complete. I think I can complete it today. Then you do some problems. I hope you have already did some reading on it. But the non-random parameter, generally you will think this is less complicated, but this is where a lot of ideas come in. The core of this course, at least the way I have designed the course, is here. You will pick up a lot of ideas here new in this one. So then after we finish that, this itself could be a course. I think in statistics this is a course. So essentially it's going to be a lot of statistics. And so if you pay attention for 2-3 weeks and you do the problems, then we will move away from this and we'll go into all these ideas, but bringing in time, T-I-M-E, time into this. Because look, you could also say that a signal is unknown, right? So you could do the same thing. So what is the difference between this and this? This is not a function of time. This is a function of time. Again, all this goes on. You can have multiple signals. You can have the signal is a random signal or a non-random signal. So then of course, you can try to see how the ideas we have developed here could be generalized to these problems. Okay. So once you bring in time, you bring in stochastic processes. So we go that route, right? So when we say, so today is a random parameter estimation. I mean, I have motivated you with all sorts of examples, right? So when you say the parameter theta is random, all it means is that the theta also has some density function. That's the main feature of a random variable. Now, of course, this may be known, may be unknown. If it is unknown, of course, it becomes an estimation within an estimation, right? So initially, we are going to assume that if it is a random parameter, we know the density function. Okay. So sometimes I use theta, sometimes I use A. The book uses different notations, of course, whatever it is. We are referring to one single parameter today. A couple of weeks I'll get into this multiple parameter. So there, of course, you can, even here there are interesting problems, right? Suppose you have n parameters. Initially you can consider that only one is unknown, other things are known. So essentially one parameter is unknown, right? So then we know how to estimate them. Then suppose you relax and say, now I do not know two parameters. I find estimate, then of course I need to find the estimators for both of them, theta 1 and theta 2. Then the question is, remember now you have two situations. Theta 1 is unknown, that's one case, you get an estimator. In the second case, theta 1 and theta 2 are unknown, so you get two estimators. So you can say, like, can I compare these two estimators for theta 1 hat, which one is better, etc. So a lot of problems will come to it. It again, at this point, as I said, it all depends on your interest also. If you find some topics are interesting, then you should read more into it. Remember, you are estimating from what? So you, of course, you need observations, right? So this is the way the problem goes. Observations are a set of observations, R1, R2, etc., Rn. So, of course, estimate the unknown. Always the philosophy is the same, right? Estimate the unknown, whether it is random or non-random. Based on the available data, right? That's known, right? So we will make this notation, right? It is clear to you, right? I don't want to use a different symbol. So this is your estimator. So remember, theta or a, whatever is the unknown, a hat denotes that it's estimator. And this is just showing that, of course, the estimator is only a function of data, right? Because the data is the only quantity that is known to you. This is unknown. This will be a function of, so we are trying to find out the, of course we want, we are always greedy, we want the best estimator. So then you can ask again, best in what sense, right? So we had, so you need, in some criterion, so of course we bring in error. Error is what? The difference between your unknown and the estimator. Right? So you can then you can generate a function using the error. Generally, it is a cost function. So what is the, so error, of course, you do want to minimize, so, or a function of error. So what comes to your mind in terms of a function? When you minimize the error, what do we generally go for? Huh? What did you say? Minimum. Minimum of what? Yeah, generally mean squared error, right? So, but it doesn't have to be mean squared error. So I am going to write something like this. So this is clear, right? This is generally you can say there is some cost function based on the error. Okay.
Professor, can you use a darker marker? It's really it's
okay. Yeah. Let me see. So like in the detection case, we could have a cost function. So remember, look here, this is a random variable, these are certainly random variables, right? This is a function of so this is a random variable. This is a function of random variables. So this cost itself, the way I have defined is a random variable. So if you want to minimize, so you really should be minimizing the average cost, right? Or expected value of C of epsilon, right? So this is your C. So this, if you want, you can always say this is the risk. So you want to minimize this. Of course, the minimization is to figuring out what is this optimum function epsilon. I mean theta hat, right? Right now, as you said, the cost function, what we are generally, we don't even think of it this way. Immediately when we say there is error, we want to minimize, all of us think about mean squared error, right? So that's only a particular, one specific cost function. So if you want this cost function, you could think of epsilon. This is the, so this is minimize mean squared error, right? Or you could also think of minimizing this. This is the, so if you draw a graph, this will look like this, right? So this is the absolute value of the error. So that will be this cost function. Or let me give you one more example, is going to be so what this says, if you want to, so this is in particular, it says so it says the cost function is 0 if the error is less than absolute value of delta, and it is 1 if absolute value of error is greater than delta. So what do I mean by all or nothing? Look, what it says is if the error is very small, look at here, if the error is very small, there is no cost. It's like saying if you're already quantizing the bits to a certain extent, if your noise is less than the quantization, it really is not going to bother you. So that's that kind of situation. Whereas if the error is beyond delta, then it's as good as going home, right? So it's a maximum. So saying that for small errors there is no penalty, but once the error is beyond a certain stage, the penalty is the same. I mean, you can draw your own cost functions. You can say that maybe this is another thing you could try out, right? You could try to work it out for this. So here you are saying that the penalty between small error and this error is gradual and so on, right? We could later, I will also think of, we will also look at the cost functions which are like this. So this is another cost function. So notice that most of these cost functions, so this is C5 of epsilon, they all have this is piece, look at it, this has different shapes. This is quadratic, whereas this is, here it is piecewise linear, then it looks like quadratic, then again at least the way I have drawn, right? So this is not one function. So a function like this you can call it convex upward, right? Whereas you don't want a cost function like this, right? Because this is not convex. What is, anyone remembers what is the property of a convex function? When do you call a function to be convex? Convex upward is this property. That means in that curve, if you take 2 points on join, the line will be above the curve. Right? So how do you characterize this? So if you take this point, let me call this point to be x1. Let me take another point x2. So I'm saying I'm going to give you the definition for convex up. So let me take a linear combination of this. Linear combination is like adding and dividing by 2. But a general linear so let me take if you add and divide by 2, you'll get somewhere here, right? Any linear combination, so I'm going to take a point, this point is alpha x1 plus 1 minus alpha x2, where alpha is between 0 and 1, right? Yes? Because if I take a alpha x1 plus 1 minus alpha x1 is going to be between x1 and x2. Alpha equal to half is the middle point, right? Right. And then you see two things to interesting. This is the property of a convex function. Evaluate, remember this is your function c. So this is c of x. So you have 3 values now, 4 values. Look at this value, this value. This is c of x1, right? This is cx1. And this is c of x2. And what about this value? Anyone? So that's c evaluated at this value. So this is c evaluated at alpha x1 plus 1 minus alpha x2, right? Right. And no. Hold on. Let me get rid of this line. Right. So look at this. This point is, let me call this point to be x0. And then of course this is c of x0, right? That's c of x0. But x0 we just said it is alpha x1 plus 1 minus alpha x2. So this value is, that value is that quantity, right? And what about this value? This value is the same linear combination between cx1 and, so this is alpha cx1 plus 1 minus alpha cx2. So now you can see if the curve is convex, this linear combination is greater than or equal to this. That's so you can say that if cx is convex, convex upward means that if you take the curve has the property that if you take 2 points and join, the line is above that. So the line is going to be alpha cx1 plus 1 minus alpha cx2 is greater than or equal to c evaluated at alpha x1 plus 1 minus alpha x2. Okay, so we will try to find out the optimum estimator for these 3, and I will also do for this. Okay. And there are results for this also. You can read up or you can try to do this yourself. Any questions so far? So before I start addressing each one of this I can write, so we can use the definition of expected value. So this is going to be the cost multiplied by, remember expected value is based on the random variables. Look at here, what are the random variables? This is a random variable, this is R is random variable, right? So this is f of theta comma R1, R2. I'm going to write it like this. This is R1, R2, etc. R d theta dr, right? And to be specific, we have decided to, remember, epsilon is going to be theta minus theta hat of r. So from here itself you can see that the random variables involved are theta and r. So I'm just rewriting. So this integral is actually an n plus 1 dimensional. This is 1 dimensional, this is n dimensional. But I won't rewrite it that way all the time. So remember, I can also write this like this, right? So the inside integral is with respect to theta. So why am I rewriting this? But look at here. The cost function is generally non-negative, right? Otherwise, remember, you don't want to write the cost as with the positive and negative, because then minimization things may get averaged out without you actually averaging. That's the reason mainly we take the mean squared error, so that whether the error is positive or negative. Because if you simply take the average of the error, that will turn out to be 0. You are not minimizing anything. So cost function is generally non-negative. Look at here. So C is generally taken to be non-negative. Any density function is non-negative. Of course, this is also non-negative. Here what I have done is I just used the conditional definition of, remember, joint density function of x comma y can be written as x given y multiplied by fy, right? So that's what so it's always true. So remember, there is minimization going on here. Minimization is with respect to what? Theta hat. And look at here, the inside, there is no theta hat here. So the minimization here is with respect to this red integral only, right? Minimization is with respect to theta hat. And so this whole quantity is non-negative, right? Look at here. So you want, then this is like summation, right? Scaling, because the density function also is a non-negative function. So it should be clear to you that minimizing this outside integral is the same as minimizing this inside integral, simply because for two reasons. For the main reason is this is a non-negative function and this whole thing is non-negative function. This argument will not go through if this function happened to be positive and negative. That is not the case here. It's like saying here, right? If you have x squared plus y squared, you want to minimize, you have to minimize each of them, right? So x equal to 0, y x squared, this is the same as minimizing x squared and minimizing y squared separately. Minimizing x squared leads to 0, minimizing y squared leads to 0 as the answer. Whereas if it is x plus y, minimizing x plus y, there are plenty of solutions. X equal to minus y, x equal to 1, y equal to minus 1 is a solution, etc. All right, so the whole point is, because this is non-negative, this problem is equivalent to minimizing this R1, which is just the inside integral. So that is C of theta minus theta hat. So of course the R1 is a function of R, right? So if you want, you can rewrite all this as that. So if you want to rewrite it, so this will be same as integral R1 of R multiplied by FR dr. I explained to you last time, right? Even though I use this F, it should be, this is of course the conditional density function of theta. This is a different F. This is the joint density function of all the random variables, right? So you can write it like this. So the minimization is on R, right? Because the minimization is with respect to theta hat, and theta hat is only here. So this philosophy goes for any cost function. So what we want to, once we, so the problem is minimize R1, which is a function of theta hat and R, so that's integral C of theta minus theta hat R multiplied by f of theta given R d. I think the book uses, I could have used the same, book uses the, instead of theta it uses the variable a symbol A, right? So theta is the unknown quantity. All right, now let me, so this is as far the theory goes. Now I am going to use each of these and substitute it and see what happens. Okay. So let's take the first criterion. We want to minimize minimization of mean square error. This is known as MMSE. Okay. With these letters, right? So remember that means C epsilon is epsilon squared, that's right. So our R1 is going to be integral of what is it, theta minus theta hat R squared f of theta given R d theta, right? We want to minimize this with respect to theta hat. Right? Now look here, this means, look at how to read this, that R1, R2 are random variables, but here we are looking at the randomness is only due to theta, right? Because the conditional density function of theta, given that this R1, R2, etc. are specific observations. So these are given values. So these are given values. So this minimization you can do because these are given values. This is an unknown. This is of course an unknown constant. So we take the derivative with respect to this unknown constant, and it's a standard procedure. So this turns out to be theta minus theta hat. Theta hat is what you are looking for. Square is gone, and then take the derivative with respect to this. So that's another minus 1, right? F of theta given R d theta equal to 0. So I see two terms, minus 2 goes away, and so I see that the one integral is the theta hat R, f of theta given R d theta equals, the other side it is theta multiplied by f of theta given R d theta. Remember the integration is with respect to theta. That's the, see, look at here. In this one, the integration is with respect to both the theta and R. We don't want to deal with all the n+1 random variables at a time. So we just realize that we can do the minimization with respect to this one random variable, which is theta. So if you look at this unknown quantity, this is not a function of theta. This is only a function of R, and R is given. So that's like a constant that goes outside, right? See, when R is given, this is an unknown constant. We just don't know what it is, but it is certainly not a theta. So it goes outside. So we can write this as theta hat of R multiplied by a density function, right? What is the value of this? Area under any density function. So that's 1. So this is equal to, this is theta multiplied by f theta given R. What do you call this quantity? Anyone? That's just the mean value, but it is the conditional mean because it's the mean value of theta given R. So of course the notation is, again, the notions we have studied in probability. So this is expected value of theta given R. Look, we have the result. This is what we have been looking for. We didn't, so we have, I'm going to write this as theta hat MMSE. Why? Because there are various estimators. So remember, saying that give me the best estimator doesn't mean anything. I mean, it means something. You also have to give the cost function. Here the cost function is minimization of the mean square error. So this estimator is MMSE, right? So this is a very classic result. The best estimator, which minimizes the mean squared error, is the conditional mean of the unknown given the data. So of course you read this as conditional mean of unknown parameter given the data. I immediately want to do an example, but I'm going to stop that temptation and let me derive all the three estimators, then we'll do an example and do various, we will see different estimators, what their connections, etc. So what will this be a function of? When you do, everything is done, and then what will this be a function of? Anyone? What will this turn out to be? Huh? R. Because remember, look at here, theta gets integrated out. Remember, you don't want an estimator in terms of theta because that will be like catch 22, right? Theta is what we are trying to figure out. So we certainly want estimate, I remember I wrote earlier, we want the estimator in terms of what you observe, which is the data. And of course we want the best estimator. Then the question is, what is best? So we said, suppose we say the best is minimization of the mean squared error, and then this is then nothing more, nothing less. Okay. And so just another observation is that in general this estimator may be maybe or can be non-linear. There is no reason to expect that so the best estimator can be non-linear. So if you want to see, let me sort of cook up a simpler example which we do in probability class. All right, so maybe this will work out, I don't know, we'll see. So I'm saying consider the case where the joint density function of x and y is k times x plus y when x and y belongs to this region. Let's make it simple, and it is 0 otherwise, okay. So let's say theta is y, x is your, so you observe data and y is unknown. So you want to estimate y in terms of x, right? You want to find out the where, so of course we want y hat, right? MMSE. From here it is, we just found out, right? This is the best estimator. We just did. So the best estimator is the conditional mean of the unknown given the data. Data happens to be x here. So we want expected value of y given x, right? So that's going to be y multiplied by f y given x dy, right? And of course you have the joint density function in this case. So we can find the conditional density function, right? So we want f y given x. As you know, that is f x comma y divided by fx, right? So this is f y given x. And how about f of x? And f of x is, you integrate out fxy, right? You integrate out y. So look here, x is given. So when x is given, y goes here. Y doesn't go from 0 to 1. So y go, and what is the expression for this line? Anyone? What did you say? Yeah, this line is of course x plus y equal to 1, right? So if y goes from, y is here 0, and at this point as he says y is 1 minus x, right? So the limits on y. See, even such a simple problem, so the limits will, remember I need to integrate out y, so y goes from 0 to 1 minus x. But this is given to us. I mean, this may not come out to be nonlinear, I am just trying it out. Let's see what it is. So this is k x plus y dy 0 to 1 minus x. So this is k. So remember, there are two terms. What is the integral of the first one? Let's see who can integrate this. So x dy, what's the integral? Right. And the next term? 2. Now you need to substitute 0 and 1 minus x, right? Remember x dy, integration is, so x is a constant, that's what he is saying, right? So remember two integrals, so x dy integral is xy, then y dy integral is y squared by 2. Then we substitute the limits. So the top limit is k multiplied by, remember the limit, I am substituting for what? Only y, right? So this is x multiplied by 1 minus x plus 1 minus x the whole squared by 2, right? Minus 0, so this is k multiplied by x minus x squared plus 1 plus x squared minus 2x by 2, right? So that's k multiplied by 1 minus x squared by 2, I guess, right? Is that right? I hope, right? This is 2, this is x cancels, so that's correct. So if I substitute it here, here you have k multiplied by x plus y, and there k multiplied by 1 minus x squared by 2. So this is 2 multiplied by x plus y over 1 minus x squared. And remember, x is given. So if x is given, y goes only between 0 and 1 minus x, and x itself, these are the limits, goes between 0 and 1, right? Hello? Anyone is checking? Yeah. You? This side, anybody? All right, so we got this, so we can plug this into this density function. So let me do it here. So if I plug this in here, integral, remember, so you have y, this density function I just found out. So this is 2 multiplied by x plus y over 1 minus x squared. Integration is with respect to y. And what are the limits on y? Anyone? On this side? What should I put here? 0 to 1? Right, look at here, it's written here. Remember, this is conditional. Conditional means what? X is given, look here. X is given. So if x is given, y doesn't go from 0 to 1, y only moves here, right? Because for a given value of x, this is the only non-zero value, everywhere else it is 0. So this is an interesting problem. So the limits are 0 to 1 minus x. Again, if to few of you, if this looks a little complicated, check into chapter 6, there are similar problems. But anyway, let's just complete this. And so if you, so this is 1 minus x squared goes outside, right? Because the integration is with respect to y. So now you just need to do this again. So y2 goes outside, right? So you have so you have xy plus y squared dy, right? So let me, so if I do this, this is 2 over 1 minus x squared. That integral is, what is it? and then you have to substitute 0, 1 minus x, right? So this is 2 multiplied by, this is bad news, it doesn't seem to be, maybe okay. So this is y equal to 1 minus x goes outside, squared. Here you have 1 minus x squared. Then here you have x multiplied by 1 minus x plus 1 minus x, I think, right? By 2 by 3. Is that right so far? Did I make a mistake? Or?
Yeah, the first term is just x over 2 because you pulled out the 1 minus x squared. The first term in the bracket.
Here?
No. Afterwards? Yeah, bracket. It's only x over 2 because you pulled out 1 minus x squared.
X over 2? Oh.
Yeah, only.
Yeah, you're right. Yeah. All right, so you see here, this you can write it as 1 minus x multiplied by 1 plus x, right? So the answer is 2 multiplied by 1 minus x over 1 plus x. And if you add it up, what do you get? 3x, 2x, 1 minus x or 1 plus x?
X plus 2 over 6 inside.
What is it? So this is 3x plus 2 minus 2x over 6, right? So what is it? Yeah, x plus 2 over 6. My whole point is, this is your estimator. So of course you are not going to guess it, right? Moreover, look at it. It's a good example. It's a linear or non-linear? In x. So it's a non-linear estimator. So remember what the problem was. Somehow you make an observation. Observation is x. You want to estimate y. So this is your, look at here. This is your estimator. We just did this. So we are saying that our estimator based on x is this. So it's a highly non-linear, okay? But to do a problem like this, you need to, you can't just run into exam and do this, right? So you need to practice out a few problems. I'll make up, I know somebody, there was a comment, feedback given to me saying that homeworks need to line up with what is going on in class, which is true. So I'll try to make up some problems like this and email it to all of you. You need to fix your email. All right, now as I said, if for a few of you, if this is looking too much details, similar problems are solved in my notes, which is on the web, right? Lecture notes, I gave you the lecture 6. Or more importantly, in Papolis chapter 6, towards the end, there are a few examples on this conditional mean. A classic problem. So here is a simple, even if it is simple, it makes the point. Just because the estimators, as I said, may turn out to be nonlinear. Nonlinear in what? Nonlinear in, of course, your observations. Nonlinear in your data, right? Because it's going to be a function of, remember, estimator is a function of data, and so I can digress here and maybe talk a little. So you may say, oh, then what about, suppose I am not interested in nonlinear estimator because it is too messy or whatever. How about linear estimators? You are going to say something?
Excuse me, I'm not sure whether I should ask this question, but if we have multiple observation, I mean x is a vector, how can we form the y hat?
I mean, it's the same thing, right? It's just going to be complicated. So suppose you have, then you need, so you will need to find out the joint density function of, the same principle is the same. You need, if you have multiple observations, you need to either know or estimate one way or the other way. You need to know the joint density function of y given the data, and then you go through the same procedure. Here instead of 1x, you may get many x's, right? So what it is, you have to figure out from the problem, right? So the easiest way is maybe take 3 random variables and assume 2 of them are, you have a data and the other one is unknown, and you follow the same procedure. But the point is, that's what it says here. but the thing to remember is somewhere here, right? Ultimately, the estimator is going to be a function of data. Conditional mean. See here, conditional mean happens to be a function of data. Data is x. It's a function of data. If data is x1 and x2, it will turn out to be a different function. Which function? It depends on the joint density function. Remember, what is this? This means integral theta multiplied by theta comma r1, r2, etc., rn d theta. You need to do this. So you need to know this joint density function. In this case I gave you, we just did a simple case, theta is y, this is x, just 2. That's the problem that I just solved. Okay. So if you have more data, x1, x2, etc., xn, you need to figure out this density function either from the context of your problem, or, so that's another drawback with this. So you may say, look, there is no way I will know this. Then you can't do anything. If you don't know the joint density function, you cannot compute the conditional mean, right? I'm sorry, so this is the conditional, right? So you want, look at here, this is the conditional mean, that means the density function of theta given all the data. But it's the,
So that function,
so let me make it very clear. In other words, what I'm trying to say is theta hat MMSE is integral or it is the expected value of theta given r. That means it is integral theta f of theta given r1 etc. r d theta. So you need to know this, but from Bayes' theorem you also know that f of theta given r is of course f of theta comma r, right, divided by fr, right? But that's also the same as f of theta comma r divided by integral f theta comma r d theta, right? So fr is the same as integrate out theta. So bottom line is you need the joint density function of the unknown and the data. Once you have this, you can find this, then you divide this by this, you get this, then you plug it in here, you get the conditional mean. Okay? All right, so the drawback is, as he just pointed out, you need to have this information. If you don't have this information, you cannot find it. And even if you do that, as this example says, the estimator may turn out to be a nonlinear. So at this point, you could say, if you want, that give me the, how do we find, everything being the same, but I'm only interested in linear estimators. Okay. That's also interesting, so maybe let me, before I go into the second problem, so this is best linear estimate. So best is in the MMSE sense, okay. Best is, we are still minimizing the right, this is what we mean by linear estimator, right? I put a L here because previously, look at here, this could be nonlinear, right? This may turn out to be nonlinear, but now I am specifically interested, so what are the unknowns here? Anybody? Data is known, so what is that we need to find out here? Yeah, of course we need to find out the AI. So again, I look at the linear error, which is theta minus theta hat L. So remember, we said MMSE, so I am going to minimize the expected value of epsilon L squared, right? So we went through all this, right? So we have, so the condition is exactly same. We minimizing all this instead. You can, so you plug it in this, it will come out to be the same way. and what is it, epsilon L squared F theta comma R d theta dr. But we realize that instead of doing this, we can simply do R1. So let me pick up that one. So R1 says or we can, I don't even have to, that's fine also, but we can do it, in this case it's even simpler. So let me put this as epsilon minus summation ai ri, right, I equal to 1 through n squared. Right? So remember here the minimization is with respect to all the ai's, right, or aj's, because they are the unknowns. And aj's are uncoupled from ri, whereas here this is a function which we didn't know here, whereas here the function is known, it is just a linear function. So of course if this is a quantity, you want to minimize, you take the derivative of this with respect to the unknowns and equate it to 0. So this is 2, then minus 1, expected value of theta, remember expected value is a linear operation, so derivative goes inside. So this is ai ri, 2 goes outside, minus 1 goes outside, and the derivative of, then you have to take the derivative of aj. So what is the term, what is the multiplier for aj? Something is missing, multiplied by, anybody? Minus already came outside, then how do you take the derivative of this? R? R, no, look at here. Summation, but there is only one term, you only need to take the derivative with respect to aj. So what multiplies rj? So that's what it is, right? In the complex case actually it is because this is absolute value squared, so this should be equal to 0. So we can ignore the 2 and minus 1, so you see 2 terms. So you say, so let me rewrite it, so it will turn out to be summation ai expected value of ri rj star minus, so I'm going to take the minus to the other side, so this is equal to expected value of theta rj hat. But this you have to do for j equal to 1 through n. We will do this a bit later, but here also it may make sense. Okay. J equal to 1 through n, right? J is what we, see here we decided to take the derivative with respect to j. So we have to do this for j equal to 1 through all the unknowns. So my point is, we have n equations and n unknowns. I'll particularly talk about this linear estimation, especially when we go to stochastic processes, so I don't want to spend too much time here. So for example, if I call this quantities to be Cij, and let me call this quantity to be gamma j, then you see I have a set of equations which I can write it in matrix form, a1, a2, etc., an, and this is c11, etc., c1n. Anybody has any questions? What is the?
Why there is j? It must be r.
Yeah, you're right, you're right. I made a mistake. So this is, you're right, this is I equal to 1 through n, right? I was. So this is I equal to 1 through n. And so this of course will, if you want, this reads now ai or Cij ai, I equal to 1 through n equal to gamma j. But j goes from 1 through n, right? And that's what I wrote there. So that's a matrix equation. I mean, of course, you don't have to write, but if you write it as a matrix equation and you call this to be gamma and this to be an A vector, then of course you can solve for A. If the C is invertible, it is this, right? And so on, right? So this is your, this A is your optimum MMSE coefficients, except this is the linear case. So remember, so look at this. So you understand, right? So this, here the problem was to, somewhere here, problem was to find out, look at here. Problem was to find out this AIs. I found these AIs. AI, where is the data now? You don't see the data. Look at here. If you look into CIJs, what is CIJ? Is the expected, so that depends on the correlation between RI and RJ. I mean, it's a little more involved. And as I said, I'll come to this in a little more detail a bit later. But so here what is this? What is this gammas? It's the correlation between your unknown quantity and the data. It's a correlation, right? Expected value is a correlation. So the whole point, so the correlations are constants. These are constants. So if you don't know, you estimate them. Again, estimation within estimation. But point is you can get the A hat. So this A, because since I have found them, I'm going to simply put a hat to show that this is, when I put this hat, I'm talking about this optimal values. Somewhere here this is unknown, here it is known. Why is it known? Because it is here. You see, A hat is C inverse gamma. Okay, so these A's are known, data is there, so you have the linear estimators. So in another case, you have the nonlinear estimator, which will be the expected value of theta given. So this is where we are with respect to MMSE. This is linear, best linear. This is what? Maybe linear, maybe nonlinear. It can be nonlinear, okay? So remember, we covered a lot of stuff. We are using the same criterion, minimization of the mean squared error. If you insist on linear, you will get this estimator. If you don't insist on linear, the best estimator is this for that criterion. Which is superior? This is superior or this is superior? Anyone? Bottom one, because here there is no restriction. Both of them are using the minimization of the mean squared error. So if you look at the variance, you should expect that. So something you can try to prove. Can you prove that the variance of this is smaller than the variance of this estimator? Okay. That is always true. So then a question comes up is there any case where, so generally it pays to do the nonlinear because this may be a superior estimator. So the question is there any case where the linear is the same as the nonlinear? The answer is yes. And so when does it happen? So let me state that result. I can prove it, but it's going to take time. I did write notes, but so let me give you. Yes?
Is there any chance that matrix C is air conditioned?
Of course. So this, as he says, if your data is bad, that's why data collection has to be careful. Suppose you collected R1, okay? You collected some data. Now you go and collect some other data, R2. But suppose you have been sloppy or contaminated so that R2 is same as R1, then there is no new information, right? So if you, so imagine this two case, say just let's take two cases. We only have two data cases, R1 squared, R1, R2. So this will be expected value of R1, R2, expected value of R2 squared. Let's say your R2 is, you didn't know this, but you collected just a, amplified version of R1. So you wasted time, you didn't collect any new information. So this is completely coherent data, correlated data. So if you look at the C matrix, it is going to turn out to be 1 alpha, 1, what is it? 1 alpha, alpha, alpha squared, right? What is the rank of this matrix? You look at 1, because you can write this as 1 alpha multiplied by 1 alpha, right? So this is not invertible, but your problem is with you collected bad data. So you go back and, so this is where the whole problem of design of experiments come in. Remember, garbage in, garbage out. So if you don't pay attention, then you're not going to get good estimators. To answer your question directly, it is conceivable that this matrix could be ill-conditioned. All that means is your data set is not as good as you expected, so you may have to go and shrink the data. You may have to find a subset of this data where it is properly invertible and you have to use a reduced data set, or you go and collect new data. Right, so that's, see, you can also see from here, if you say I want it to be most conditioned, you know that the data should be uncorrelated. It also tells you. Then you can have a diagonal matrix, right? So that means if you collect the data, if you make sure that the data has nothing to do with each other or independent, then you are always guaranteed that you will have, what? Diagonal or at least full rank matrix. Some correlation may be okay, but complete correlation is useless, at least for this problem. So this says generally the nonlinear estimator is superior to the linear estimator, right? A hat, of course, is given by this C inverse gamma. I went through this, right? This A hat is the same as here. That's the linear estimator, right? So I'm going to give you one case where there is an exception. All right, so this is the result. Let me try to prove it maybe in 5-10 minutes, or we can do it later. I do have the proof written up for you. So maybe I'll sort of run through it and then you read it at home. So let me give you a handout. So pass it on to both the sides. Or you can read it at home. Maybe you can, let me sketch the proof quickly. So look, everybody got a handout, right? So maybe you can look at the handout and here, so I'll be quick. So listen to the key point. This is, what you need is, remember, this is unknown, this is known. This is what you collect, right? Data you collect. This is the parameter you are interested in. You are assuming that they are jointly Gaussian and they are zero mean. If any one of this condition is not true, then what I say is not true. Okay. So we know theta, we of course know that theta hat is, this is the best estimator, right? This is the best nonlinear estimator, right? And similarly, we know that the best linear estimator is summation ai hat ri, right? I equal to 1 through n. How is the ai hat? Ai hat is such that the error, which is theta minus theta hat, which is theta hat L, which is theta minus sigma ai ri, right? Is all right. So I forgot to mention the key property here. So all this is well and good. When we were doing the linear estimator, remember you can check, we had this equation with you, right? I said this is equal to 0, right? Hello, you remember? But let me make one observation. I forgot the punchline. This is error, right? Right? So if you rewrite this, this is the most important. So this is error. This now says this error is ERJ star is 0. J equal to 1 through n. This is in linear estimation, okay? We had this expression multiplied by -2, it doesn't matter. This quantity is E, right? This is E, right, this quantity. So you get this expression. Look at what it says. This says when you are optimal, what is this? When do you say two random variables, expected value of xy equal to 0? What is that property? Anybody? Orthogonalities. That means when you are optimum, the error is orthogonal to the data. So error so this is your E. All data sets, look, any data, so error is orthogonal to, E is orthogonal to R1, E is orthogonal to R2, etc. So this is the orthogonality principle, okay. So I was saying, so that we already derived, right? So this is something we'll come back also, but this is the rule. If you are for the linear estimator, the rule is error is orthogonal to the data, all data points. So let's use it here. So what I want to show is, I want to show these two estimators are the same. These two estimators are the same, right? So I'm going to use that property here. Remember, this is of course linear error, right? We are talking about linear case, not non-linear, linear case. Since it is linear case, you don't need L, etc., but I'm just saying, right? So error is orthogonal to all the data vectors, right? I can write it like this, right? This error is orthogonal to R1, R2, etc., Rn. This is just n equations. I just wrote a notation here. Anybody? Any problem? All right. But you see, what is the expected value of what is the expected value of epsilon L? Look at here. What is the expected value of epsilon L? Anybody? This one is expected value of this, which is 0, right? Somewhere here. And all the Ri's are 0 mean. So expected value of epsilon L is 0, and expected value of R is 0, right? So this is 0. So yes, certainly I can write this as, this is the key. Yes? So what do you call this property? If two random variables are expected value of xy is the same as expected value of x multiplied by expected value of y, what do you call that? Uncorrelated, right? But epsilon and r are Gaussian. So uncorrelated is the same as, all right, you happen to be right, but right. So this means these random epsilon EL and all the data vectors are uncorrelated. But as I said, they are also, as you said, it's also, they are also independent. So we have, but look at here, look here, this is Gaussian, all these are jointly Gaussian. Functions, linear functions of Gaussian random variables is Gaussian. So this is Gaussian, right, or normal. And data is of course Gaussian. So these two are also Gaussian, right? This is Gaussian, this is Gaussian, this is given to be Gaussian. So two Gaussian random variables which are uncorrelated are also independent. So what are the random variables that is independent? This random variable, the error is independent and are independent. So anybody, what happens if I take, if x and y are independent, what happens to expected value of x given y? Anyone? It's simply x. So let's say this is your x, this is your y. So we get expected value of epsilon L given R, of course, is the same as expected value of epsilon L. But epsilon L expected value is what? You're sure? Of course it is written there, right? 0, right? All right. Now, so let me put this side for expected value of epsilon L. Epsilon L is what? Somewhere here. Where is it? Here. Theta minus theta L hat given R. So of course this side you can write it as expected value of theta given R minus expected value of theta L hat given R, okay, is 0. You need to go home and there are several arguments going on. Now let's concentrate here. What is this? So this I'm just going to write that expected value of epsilon given R equals, of course, this side, right? Equals expected value of theta L hat given R. But theta L hat is what? Expected value of sigma AI hat Ri given R. So this quantity given R is what? R is given. So then this quantity is not a random variable. So that goes outside, right? So that's the same as sigma AI hat Ri, I equal to 1 through n. But that's the same as theta hat L. What is this quantity? Anybody? That's your theta hat nonlinear estimator. Look at what we have proved. We have proved that theta hat nonlinear estimator is the same as theta hat linear estimator for Gaussian. I used the Gaussian property several times, so you have to go and look at all the arguments. Of course, this is a well-known result. What this means is if the data and the unknown quantities are jointly Gaussian, you can simply worry about the linear estimator. By trying nonlinear, you are not going to get anything better. All right, so that's good about any questions? So hold on, this also tells you that Remember, look here, you know that the best nonlinear estimator is the conditional mean, and the conditional mean is linear. So this tells you that if you have any set of joint Gaussian random variables, and if you try to find the conditional mean of any one of them with respect to the others, it will be always a linear function, right, from here. Any questions? Otherwise, I'm going to go and quickly finish the other two estimators, then we'll do some problems. Remember, so far I've only been talking about this for the last 1 hour. So let me talk about the other two also. Remember, you're in radar, swirling model, etc., swirling 1, swirling 2, so those parameters are random there. I mean, of course, this is obvious. Something is unknown, you want to estimate the unknown in terms of the known quantities, right? But the unknown also happens to be random. As I said, next week onwards, we will look at unknown being also non-random. So again, the same thing, we have error, right? Error is, of course, theta minus your estimator. We went through all this, right? We find a cost function. Minimum cost function is a random variable. So we try to find the average value of the cost function, which is the risk. And then we said that it's enough to do the inside one, right? You can minimize the R1. Remember, minimization is over theta hat. So cost function is, what is it? Theta minus theta hat R multiplied by f theta given R d theta. This is where we were before. So except that I'm going to replace this cost function as, this is the second one, right? Absolute value of the error, theta minus theta hat R is, in other words, we are considering the case where C epsilon is absolute value of epsilon. So we want to minimize so this quantity, right? I can write it here. So if you want, you can plug in, or let me plug this in here. So minimize R1, which is theta minus theta hat R multiplied by f theta given R d theta. Because of the absolute value, we cannot immediately jump in and take the derivative. So I can write this as two integrals, right? Remember, what is the variable? Theta is the variable, and theta hat is somewhere. So when theta goes from minus infinity to theta hat, right? Minus infinity to here, and then from theta hat to infinity. So when theta is somewhere here, which this will be written as what? Remember, it is the absolute value. That means it's the larger value. What is it? This is theta hat minus theta, right? And here theta is here. That means it is it's the other way?
Yeah. No, this is good. No, that was good.
Look, which right, you are right. And here theta is here, so this is theta minus theta hat. F. Thank you. Right, that's good. So we want to, you understand why I did all this? Because I wanted to get rid of this absolute value sign. See, there is no absolute value sign here because this is positive in that region, right? Now I can take the derivative with respect to theta hat. And this is where you have to use this rule I gave you a couple of weeks back, remember. So I need to take the minimization is with respect to theta hat, so I need to do this. Remember, theta hat is not at this point because r is given, this is just an unknown, so we can take the derivative. You remember this? I said if h of x is ax to bx g x comma y dy, then derivative of hx with respect to x. You take the top derivative of the top function, then you substitute wherever the variable of integration is the top function, minus the derivative of the bottom function, same thing, substitute, then leave the limits as they are a, b, take the derivative of this with respect to so the derivative of the top limit with respect to theta hat, what do you get? 1. And then when you substitute, remember the variable is theta, when you substitute, what do you get? 0? Go 0, right? Because this goes away. Otherwise it will be theta hat given r, right, multiplied by 0. So the first term is 1 multiplied by 0. Second term is the derivative of a constant, so that also doesn't contribute. The third term is we need to take the derivative of this with respect to theta hat. So what is there is no theta hat, so this is a constant. So derivative of this with respect to theta hat, remember the limits stay as it is, so it's minus infinity to theta hat. And what is the derivative of this with respect to theta hat? 1, right? So 1 multiplied by whatever is the constant. So we just finished with this term, okay? Plus same thing here, derivative of the top limit with respect to, that's a constant. Minus the derivative of this with respect to theta hat, that's 1. But then when you substitute it here, you get 0, so that doesn't have any contribution. I hope you see what the derivative of this is 1, right? But when I take this limit and plug it in here, here of course as I said you get f theta hat given r multiplied by 0, so no contribution, right? Because theta hat minus theta hat, 0. So the second term also no contribution. So then the third term is you leave the limits as they are and take the derivative of this with respect to theta hat. What do you get? Look at there. Derivative is only here, so that's minus 1, right? With respect to theta hat, so that's minus 1. Minus 1 multiplied by whatever is there, that's a constant. This should be equal to 0 because you equate the derivative to 0. So let me clean up all this stuff. So essentially you get, remember what is that you are looking for? You are looking for theta hat. So theta hat satisfies this highly nonlinear equation. But you are familiar with this, so I took one term to the other side. So if you have a, look at what it says, it looks complicated, but once you, I have a density function, right? So I have some density function, right? A density function is like this, right? So this is the density function of theta given r. What are we saying? I want to find out some point such that the area from minus infinity to that point is the same as the area on the other side. So how much is each of these integral? Anyone?
0.5.
You see it? Whole integral is what? What is the area under the whole density function? 1. So we want to divide that equally, right? So each is 0.5. So it may be somewhere here. This theta hat is such that I want this area to be half, and I also want this. What do you call this point? Anyone? Such a point in a density function has a name. Yeah, it's the median. So bottom line is, of course it's a nonlinear function, but what you are looking for is the median, right? So if you use this, so remember, depending on the, it's not always enough to say I want the best estimator. If you use this criterion, you get MMSE estimator. You use the absolute value, you are getting now the, so here you are getting the conditional mean as the estimator. Here you are getting the conditional median. Why conditional? Because look at the density function. You are dealing with the conditional density function. So this theta hat, of course, is going to be a function of R. It is going to be the median. So here I can write each of them must be equal to half. That means the theta hat right? So it's the median of the median of the density function. Okay. ABS saying that this is the, of course it will be a function of data. I'm using the absolute value as the criterion. Okay, so let's go to the last one. So let me summarize here. This means we know the result, right? So quadratic condition, here the best estimator is expected value of theta given the data. That's the mean. If you use this, this is the median of the density function. So this is of course the conditional mean. So let's look at the third one. Any questions? So we are moving along. So remember, so just saying give me the best estimator has no meaning. Best estimator in some context. So if the error is small, the cost is 0, and if the error is small, so that means smaller than some delta, the cost is 0. Otherwise, otherwise high penalty. So we want to find out what is the best estimator for this particular cost function. So again, once again, R1 is what? R1 is cost of error, right? F of theta given R, right? Again, of course, we want to minimize this by picking up theta hat. Where is theta hat? Theta hat is here because this is the same as, so somewhere here I'll do, right? Theta hat is coming on. Epsilon is theta minus theta hat, right? So look at the cost function. Cost function is now like this, right? So this cost function, I can also rewrite slightly differently, right? right? I'm saying something like this is a constant, this minus this, right, symbolically, right? So this is the cost function, I should plug it in here, right? So this is your, so isn't this true now? So consequently, from here you can also write R1 as, so look here for a second. This function is what this C represents, hello? This function is what this C represents. So I'm going to, instead of that, I'm going to write that function as this function minus this function. So remember, this is minus delta, this is delta, this is minus delta, this is delta. So if I put this function, that's like 1 multiplied by the whole density function. What do you get? 1. Minus this function multiplied by this. So that's easy. So I can write this as 1 minus, isn't this? So this function is from minus delta to delta 1 multiplied by the density function of theta given R d theta, right? You see what is going on? It's very easy to understand, right? What happened to C? There is no C here. I just absorbed it. C is 1, right? Oh, in this case, this is your C. This C can be written as symbolically 1 minus this function, right? So 1 multiplied by any density function is 1. This function means this is 1 multiplied by the density function, but from minus delta to plus delta only, right?
Minus delta to delta is a range of decimal, right?
Minus delta to delta is from here. Nothing to do with density function. Density function is like this. So what is the question? I am answering even before I hear the question.
I mean, the range from minus delta to delta is the cost is the range of the variable cost function.
Yeah, from minus delta to delta, the cost function is 1. So it is 1 multiplied by that. Is that what you're saying? Look.
I mean, the range of theta is different from the range of the cost function. So
Remember, we went through all this. Remember, you have 2 random variables, right? R and theta. Look at the board which has gone away, somewhere here. Before you had a theta R, we conditioned on R, remember?
yeah.
So then we decided that it is enough to minimize R1. So the joint minimization is done. We minimize this, then you plug it in here, you get this. All right, so hold on. If you look here, this theta is, it's not a big deal. Theta is of course what? Epsilon plus theta hat, right? So you can do a very simple transformation, right?
Yeah.
And you can also rewrite this as, hold on. So this is theta, right?
Yeah. So range.
So you just make a new, if you want, then rewrite theta as, so this also tells you epsilon is, so you define a new random variable, epsilon equal to theta minus theta hat, right? Then what is the density function? That's very simple, right?
No, I don't mean the density function, I mean the range.
No, I'm saying, so let me bring this in terms of epsilon. This is epsilon, right?
Yeah.
Right? So let's keep it simple. You listen, I'll make it simple for you. So I can also rewrite this using a new different density function if you want. Remember, it's a different density function. Hello, you pay attention here. I mean, I'm trying to, this is a theta given R, right? So let me rewrite in terms of epsilon given R. Is that fine with you? Okay. Don't say, listen to here. C epsilon is the same, right? And this density function I'm going to rewrite in terms of another variable if you like. All right, now the arguments are the same. This function can be written as 1 minus this function, right? So that's going to be 1 minus, so all you need to do is, it's a good point, if you want, you can also write.
Yeah, that's all right.
All right, now let me, so either way is fine, so it's also, so I'll write both the ways. So just to make sure we are not dealing with the same function, or you can write this in terms of some g function.
Excuse me, Professor, he just meant that R1, the integral of theta should
All right, so then I think easiest way is here, right? So this should be,
theta hat plus and minus delta.
Yeah,
that's good also, right? Either way is good. Right, because look at here, what he, so we don't even need all this. Because epsilon is what? Epsilon is theta minus theta hat, right? So one extreme it goes to minus delta. So if you want from here, the limits on theta is theta hat minus delta, right? Do you see what is going on? See, epsilon is theta minus theta hat. In one extreme it takes the value minus delta. So what happens to theta at that point? It's going to be theta hat minus delta, which is what I put here. In another extreme it takes the value delta, so then theta becomes theta hat plus delta, right? Good point, so you are awake. So I'm going to, so how do we, you seem to be, should I explain a bit more or it's fine? So anyway, let me mention this one more time. Question is, what are the limits here, right? So remember this function goes from minus delta to delta, but this is on epsilon, but epsilon is theta minus theta hat. So put this equal to one extreme, which is minus delta. So the limit on theta is theta hat minus delta, which is what I wrote there. The other extreme is delta, so equate this to delta, then the limits on theta is theta hat plus delta, which is what I have here. Or if you don't like this, you can also rewrite in terms of, but I suggest this is the best way, I agree. So we don't have to go this way, except, so this is good. And so now we remember, so this is in terms of, this is the conditional density function. I need to find out, what do I want to do? I want to minimize this, right? Look at here. I want to minimize this on theta hat. So 1 minus this, that's the same as, what should I do on this? Minimize or maximize? Maximize, right? So I want to find out theta hat such that I want to know, criterion is maximize on theta hat. I want to find out theta hat such that this quantity is maximized. All right, here comes the punchline. Listen to me now. So question is, how do you, what is the unknown? Unknown is theta hat. So theta is here. We want to pick up theta hat somewhere. I don't know where should I pick up here? Should I pick up here? Etc. That's the question. So if you, wherever you pick up, you take a small window around that, right? That's what it says. Theta hat minus delta. So you pick up a small delta and integrate the density function. So you will get this value. If I pick up here, I take a small density function and integrate, I get this value. If I pick up theta hat here. If I pick up theta hat, I go minus delta plus delta here and I pick up and I integrate here. Which integral is the maximum? So you can clearly see that you should pick up theta hat such that wherever this density function peaks, maximum of this density function. So let me redraw all this stuff. So you may have a density function which is like this, right? It may have multiple maxima, but what it's this is your density function of theta given R. Then the right estimator seems to be, you go for the peak value, that's your theta hat, because if you go, this point is theta hat minus delta, you go this point is theta hat plus delta. So if I take a window, delta is very small, right? So delta is very small, so delta is like this, right? So if I take a window around here, this integral is of course larger than any other window I take anywhere else. So this is your optimum estimator. So this is going to be also theta, the theta hat is given the maximum value, or a probability density function, we call it the mode of the so that function is called the a posteriori PDF. What does it mean? See, this is the probability density function of theta given the observations. So you are looking for maximum, one letter here, another letter here, another letter here. So if you put it together, you get an English word map. So this estimator is known as map estimator. MAP stands for maximum a posteriori PDF. A posteriori probability density function. What is, the theta has its own density function, which may be like this. So this is called the a priori density function. Look at here, we have two density functions, both are for theta. One is its raw density function, RAW, without any data, that we call it a priori. A priori is before. Before what? Before you collect the data. So you have some initial hunch, you collect the data, then you use the data to compute this density function. How do you compute it? This is where the Bayes theorem comes in, right? So look, we did this. So this is going to be given by theta hat map. This is the mode of the density function, the a posteriori density function. This, I have notes. Let me see, we may or may not finish this class. I'm going a bit slower than generally I do. We did a lot of details. I do want to do a couple of problems rather than this one. So generally, so either you read it up, or I'll spend a little bit time next week. I mean, when we meet Monday. What was I going to say? All right, so generally this is what it is, you see. You may, if you know nothing, you can take this approach. You say that I know nothing, I know that it could be anywhere, so this is your a priori PDF, right? Like phase angle. In a unknown signal is coming, you don't know what phase, you say random phase, it could be anywhere from 0 to 2 pi, uniform, that's a clean assumption. Then you of course collect some data, or now you can, I say that I want to update my information using this, so then I get a new density function of theta given R. This is the a posteriori PDF. So that's what we need. So data is the king or the queen. You use the data to update your ignorance. This is your initial ignorance. This is what happens in machine learning. You collect the data, you start with something, then the new data comes in, you update your PDF, All the decisions are made based on this. You get new data, you again update your PDF, okay. So that's the PDF we need to use, a posteriori PDF, to get the mode. So you see mean, median, mode, depending on which criterion you use. What happens if the data is Gaussian? Right, remember, if it is Gaussian data, look at here, the density function is like this, right? So this is the mean, this is the median, that's the mode. So for the Gaussian, all the three, if the data is jointly Gaussian with the unknown, all this, everything, all the roads lead to Rome, everything, but only for Gaussian data. Otherwise, I am going to show you examples where these estimators are different. Maybe let me make up a couple more simple problems to illustrate it, then I'll email it to you. You can solve it in addition to homework, some standard problems which I give. This homework may be a bit hard, so don't try to do it the night before. You should start reading, and some of this you may be able to find the solutions in the book if you read carefully. I want you to go back and read and so on, right? You're not going to just take this and solve it. It's not that easy. But it can be solved because I'll give you the solutions next week. So let's look at some problems. So you see, how do you find the map estimator again? Mode. Mode means peak value. How do you find the peak of any function? What do you do? Take the derivative, right? So if you, one simple way to do the derivative is, you can take the derivative of the density function with respect to theta, and then equate that to 0. So this equate this to 0, and what you get is going to be theta hat map. So taking the derivative of the function is, sometimes it's easier to do the derivative with the logarithm here. So you can either do this way. So this is how you find the map estimator. Either take the derivative of the density function, because look, you can plot, if you have the density function here, if this is your density function, if remember, so you can certainly take logarithm. So your logarithm will come out to be like this. Log also is positive, and may not be positive. But it will peak. Log is like this, right? So it will peak proportionately. So this is your log of f. Let's say these are negative values because depending on the values, negative or positive, but the peaks will coincide. So either you can take the derivative with respect to the black curve or the red curve. Yes? So let's do a couple of problems, or I hope you read before you came. Now you should go back and read again. So it will make a little more sense, and start solving the problems, okay? Anyway, so here is where the Bayes theorem comes in. Look at here, machine learning, right? You have initial ignorance, then data comes in, you want to update your ignorance and find this density function. As you know, this density function now is, so I'll write it there, okay? So this is f theta given r, this is what we need. This is the same as fr given theta multiplied by f theta multiplied by fr, right? So this is your a priori, this is from your data, And this is of course the Bayes rule, right? And this is your a posteriori. Right, so if you take the logarithm, you get log of f argument theta, which is what we want. This is logarithm of f of argument theta. This is not a posteriori, this is just argument theta plus log of f theta minus log of fr. Remember, all these f's are different, right? So now if you take the derivative of this log, so if I take the derivative of this log with respect to what? With respect to what? Theta, and equate it to 0, I get the map estimator, right? That's the same as, look, taking the derivative on the right side with respect to theta. So that's logarithm of f of r given theta plus derivative of the theta log of f theta. And the derivative of this with respect to theta is 0. So you only need to take the derivative of these two terms. So either way, you can either do the left side or right side. I think it is a high time to do some examples, so I'm going to stop here and so either you can do this. As I said, this density function is never given to you. What you generally have is this density function, and this you need to figure out from the data generally. Let me do an example, then everything will become clear. And I have actually done this example for you as notes. I wrote it very fast, so but something is better than nothing, right? So I think what I am going to do here I have done, let me see what, here I have done both MMSE and you have seen this problem in the detection case. I have also done the map estimator. So MMSE is a little harder, so you can check through at home. Let me do the map estimator for a problem here. So any questions before I go into the example? Look at here. Hello. You may, so summary is like this. So initially you may have some density function for theta. Then data comes in, you have another density function of r given theta. We want to use this and the base function because look here, how do you find fr? Fr of course is the same as this f r given theta multiplied by f theta d theta, right? So once you have these two, you can find out fr, you divide, you get f theta given r, right? Machine learning, you have a priori, this is coming from the data in the context, you figure this out. Then here comes the, then using this you need to figure out f theta given r, okay? That's where you will use that relation. Then this is your map, theta hat map, okay? As I said, MMSE, of course, it's a different beast. You need to take this density function and find its mean. You just need to do it. Unless if it is not Gaussian, the map won't be the same as MMSE, as I'm going to show you through problems and so on. Any questions? Remember, we only just started estimation. You can't be It looks like you had enough already, right? So you need to do the problems and so on, right? So let me write down few problems and we'll try to do as much as you can. Anybody has any questions, ask me. So remember, map, you don't try to look at it, you use, if the density function is smooth and differentiable, you can just take the derivative of the density function or derivative of the logarithm. Or instead of this, you can also use the Bayes rule and take the derivative of the logarithm of the r given theta and f theta, right? So let me do a problem at this point. I started doing, so I'll come to that, at least you can read it. So let me do a problem which you don't have there. We'll come to that. Anyway, we have enough time, so maybe let me start with what you have in front of you. Any questions? Hello? You? No. Let's say all the data are Gaussian, okay. So theta is Gaussian with some variance. All the Ri's are Gaussian with, well, let's say I'll use the same model you have. So Ri's are of this form, A plus Ni. So A is your theta. And let me use the same notation I have used there. So you have n observations. Remember, this came in detection. Anybody remembers this, right? But the Ni's are also Gaussian with zero mean and variance sigma n squared. So you see, first conclusion is this is Gaussian, they are jointly Gaussian. In fact, let me say that these are independent. What is independent? The unknown and the noise are independent. You can call this the signal, this is the noise. Signal and noise are independent. But the data is not independent, unfortunately, because the data depends on the same signal. So that's okay. So in this case, the data is dependent data. That doesn't mean it is coherent. It's not the coherent because this thing is different, right? Noises are different. So this is not completely coherent. We don't want one observation to be multiple of the second observation, which is there is no information in it. They can be correlated, but you don't want it to be completely correlated or coherent, right? So what I have done, I don't think I will have time here. What I have done in the notes is I went ahead and found out expected value of theta given R, okay? Because this is your MMSE. It takes some time, you can look through it, then you can redo it. But I know that this is the same as map. Why is that? Anybody? Why is this two the same? Everything is Gaussian, so let's do the easiest one. Okay. Here, of course, this will involve theta multiplied by theta given, or you have to do all this integration. I have done it there, so let me do this in the interest of time. So if you want to find out theta hat map, you know that you can take the equation, we do the derivative of logarithm of f of theta given r, right? Theta is what here? A, right? And A equal to A hat map equal to 0. But remember, I said A given R, I went through all this, so there is also, if you want, you can also write it as log of R given A. Any questions? I just wrote the formula which you have earlier. Right? FA is given to be that CC. FA is 1 over square root of 2 pi sigma A squared e raised to minus A squared over 2 sigma A squared. Right? What is it, your problem? Remember, plus minus FA, the derivative is 0. And now we need FR given A. So this is where probability definitely helps you. Look at this problem. Given A, Ri behaves like the noise, and all the noises are independent. So all this is given A. So you need to be matured enough to write this. R1 given A, this is the same as R2 given A, etc. Rn given A. Again, look at the argument. If A is given, R1 has mean A and variance the same as the noise, right? N squared. So each of them have this form. Each of this looks like 1 over, this is, I'm saying, normal with mean A and variance sigma n squared. So this is 1 over 2 pi sigma n squared e raised to minus R1 minus A whole squared over 2 sigma n. If I multiply all this, I'll get this 1 over 2 pi sigma n squared to the power n by 2 e raised to minus summation Ri minus A, the whole squared over 2 sigma n squared. So let me take the logarithm and plug it in here. So here I need to take the derivative of the two logarithms, right? So I can also write this as like, look at here, a logarithm of f of R given A plus logarithm of FA equal to 0, right? I can, dA is common. So FRA given A is here. When I take the logarithm, I will do it here. So we need to do the derivative with respect to A. Let me take the logarithm of this. So this is a constant. So I have log of 2 pi sigma n squared to the power minus n by 2, right? Then this is minus summation Ri minus A the whole squared over 2 sigma n squared I equal to 1 through n. So we took care of this. Then we take the logarithm of this. So again a constant minus log square root of 2 pi sigma A squared minus A squared over 2 sigma A squared. I need to take the derivative of this with respect to A. Derivative of this is 0, derivative of this is 0. So when you take the derivative, look at here, 2 comes outside, a minus, right? Minus minus becomes plus. So what do I get? Ri minus A. 2 cancels over sigma n squared, right? N equal to 1 through n. This is after the derivative. This is gone. Here I get minus 2 cancels. A over sigma A squared equal to 0, right? So let me get rid of this if you have all that, right? today is Thursday, the whole day Monday I will be at office, so if somebody wants to meet with me, just come early or come later, either way. Now remember, you need, this is, before you equate to 0, you put A equal to A hat map. So solve for A. So A hat, so this is gives you what? N over sigma n squared, right? Plus 1 over sigma A squared multiplied by A, I'm going to replace it as A hat map and take everything else to the other side. What do you get? Equal to, so A is A hat map. Otherwise you have sigma Ri, I equal to 1 through n over sigma n squared, right? So I can solve for A hat map is equal to sigma A squared over n sigma A squared plus sigma n squared summation Ri. Look, as promised, look at here. As promised, the estimator is a linear estimator. Look here, in this case summation. So if everything is Gaussian, you should get a linear estimation of the data, on the data. Here the scaling constants are the same. If you make the variances of the noise or something unequal, you will get different constants here. You can redo it. Okay. Of course, if you want, you take this n outside and you can write, you pull out the n. So you get like this, if you want. Okay. You can also rewrite it like this. And you can pull out a so essentially it looks like 1 over 1 plus sigma n squared over sigma A squared over n, 1 over n sigma Ri. Why do I write like this? So if n is very large, this term goes to 0, and you see that the map estimator is the same as just the average value of the data. Otherwise there is a scaling factor for finite n. What is MMSE? Exactly the same thing, because it is Gaussian. But just to make sure I have done it, actually before you look at my solution, see whether you can do MMSE. And if you get stuck, then you can look at my solution. Okay. So let's do a couple more examples, or at least one more. So I'll write it there. Any questions on this? So you can make up your own problem. Let's look at this. I hope this is my observation, right? So I'm saying, lambda is unknown. In fact, I'm telling them. So lambda itself is, that's the a priori density function, right? A priori. So I give you that lambda is exponential. Then you observe the data. The data itself is exponential. So this is a double exponential problem, right? Data given lambda has an exponential behavior, right? So exponential looks like what? Like this, right? So this is your a priori. I don't know whether it makes sense. So just to give you a crude example, this is the population density of a place, maybe geographically. It depends on various values of lambda, we don't know. But the population here is some value, some value, some value. So if you observe something, then from there you want, so generally you observe R, and then you want to go back and predict lambda, right? That's the problem. So you want to predict, lambda is the unknown, so you want to predict this, right? So in this case, somehow maybe through more studies, I was able to come up with this. This is your problem. Generally, you not only you measure the data, then empirically you are using some modeling. You need to figure out this. Look at in the previous problem, I gave you the model. I said R is of the form A plus Ni. So you were able to conclude R given A was Gaussian, etc. So here I just give you a model. Of course, then you can find out MMSE, you can find out map. Let's try to find out these two and see what happens. Okay. Also, if you come up with some value for the R, from the R you remember this is generally an inverse problem. I want to figure out which area, which region of Manhattan that thing came from, right, for example. If indeed such a model occurs. Right. So this is another problem. We'll solve, see how much we can solve. So you can essentially read what I'm writing, right? So this says the data given some lambda, all the data are independent, right? Conditionally independent. And let's say each of them, I am telling that each of them is Poisson, okay? So e raised to minus lambda, lambda to the power xi over xi factorial. So there is a product sign I equal to 1 through n. So this is e raised to minus n lambda, lambda to the power xi over product of xi. So I tell you that. Now suppose, I'm just making up a problem. So I also tell you that this is exponential with some parameter mu. All right, so you take this problem home and see whether how much you can. Certainly you can find out lambda hat map is easy. Lambda hat MMSE is a bit more tricky because you have to find expected value of the conditional mean of lambda given all the x's. Okay. So same thing here. Let's find out MMSE and map. So this is expected value of lambda given R, right? There is only one R in this case. And this you know what to do, right? So try to do that problem at home. You may never be able to complete it. I haven't done it myself, but see whether you can, certainly map is easy, as I'm going to show you here. So how do you find the map estimator? Remember, don't forget, so you need to take the derivative with respect to lambda of what? What do we take the derivative with respect to? Anyone? Remember, so conceptually you need to have an idea. You have the a priori density function of lambda, the new data comes in, you get the a posteriori density function. Remember, we went through all this. That's the one, that's the key. So we need to take the density function of that, or if it helps you, take the logarithm of lambda given r, right? And equate this to 0. So whatever it is, we need to find out that density function. So we need f lambda given r. So this is where the Bayes theorem, see, you were bored when I was discussing Bayes theorem in probability, but now you can see application. So this is r given lambda multiplied by f lambda over fr. Anyway, we need this even here, right? Because look at here, this is going to be integral lambda f of lambda given r d lambda. So whatever way you need this density function, right? So this density function is required. So this is given to be exponential, this is given to be exponential. If you want to find the mean, I need to find this properly. Look at here. If you want to find this quantity, I even need to figure this out. If you only want to find the map estimator, you don't need to worry about this, because remember, when you take the logarithm, log, the minus log, when you take the derivative, that's gone with respect to lambda, because this is not a function of lambda, right? And this are given to you. So we can do the second one very easily. So let me do that, right? So this is the same as taking the derivative with respect to lambda of, from here, log of r given lambda plus a logarithm of f lambda itself, right? So you can equate this to 0 at lambda equal to lambda hat map. And look, if r given lambda is given, so let me, so this is taking the derivative of this with respect to log lambda from here, minus lambda r plus, where is the other one? Here, log c minus c lambda. We need to take the derivative and then equate to 0 with respect to lambda. So the derivative of log lambda is 1 over lambda minus r, log c is 0, minus c equal to 0, right? So what do you get? Lambda is what? All right, so lambda hat map is 1 over c plus r. So I want to show that the map estimator also can be non-linear, all right? So now let's try to find out this. Remember, this fr is going to be integral f r given lambda multiplied by f lambda d lambda. This is your fr. So let me substitute that, and so fr is what? Fr is integral. Let me substitute each one of this. So where is it? Lambda e raised to minus lambda r, c e raised to minus c lambda, d lambda, right? D what? D lambda. So that lambda goes from 0 to infinity. Why is that? Look here. Lambda is exponential, goes from 0 to infinity, right? So c goes outside, you have here lambda e raised to minus c plus r multiplied by lambda d lambda. So let me call this to be y, c plus r multiplied by lambda is y. So this is c integral 0 to infinity, same limits, re 0 to infinity. Lambda is y over c plus r, e raised to minus y. D lambda is dy over c plus r. So you get c over c plus r the whole squared. Integral 0 to infinity y e raised to minus y dy. What is the answer to this? Anyone? Yeah, that's right. You can check it out, it's just 1. Okay. So we get FR to be c over c plus r the whole squared, r positive, right? So let me plug it in here. So if that is the case, this density function turns out to be what? Let me substitute everything. R e raised to minus lambda r, c e raised to minus cr over c divided by c plus r the whole squared. Okay. All right, so we had, I'm just quoting the result here. We had lambda hat map, you had already done it, is 1 over c plus r. Right? So this is now c plus r the whole squared, lambda e raised to minus c plus r what is wrong with here? C lambda, right? So this is this density function, right? Yes? Now I need to, so if you want theta hat or lambda hat MMSE, you need to go home and finish this integral. So that's going to be expected value. Conditional mean of lambda given the data. So that's going to be integral lambda multiplied by f lambda given r. But the variable is lambda, goes from 0 to infinity. F lambda given r is here. So if I substitute that c plus r the whole squared, right, integral lambda squared e raised to minus c plus r multiplied by lambda d lambda. So again the same thing, let me substitute this to be y, so I get c plus r the whole squared. This is y over c plus r the whole squared, e raised to minus y dy over c plus r the whole squared. So in this case it turns out to be, I think, c plus r integral 0 to infinity y squared e raised to minus y dy. Anybody knows what is the answer to this? I think it is 2. So you get the answer this time is c over 2. Unless I made some mistakes. Where square? Why? Here you have, no, there is no square here, right? Here you have square, you have dy. Square cancels, you get, right? Isn't it right? But at least this is not equal to MMSE, I'm sorry, map, right? This is your MMSE estimator. True? All right, so you can try to do the, let me see whether there is any minor. You can try to do that Poisson case, right? Yeah, remember I had another problem, right? So, and I wanted to do something else, but everything cannot be, so we'll do Monday. Right? But we have a few more minutes, so let me see. Any questions first of all? So you see from here onwards, the next few classes, a lot of computation. This is how you, either you do it or you don't do it. So if you spend the time, you can come up a long way, right? You must spend the time. So details, because if your problem, remember theory is very easy, but it's the details. If you cannot do a problem, you cannot do a problem. You are not going to walk out of it by talking, right? So if you plot this density function, you can find the absolute value, right? That's easy. Because this is the density function, right? If you plot it, I think it will take some value like this, right? Because in the, where is it? Here. When lambda is 0, it is 0. Then it peaks and goes. So you can try to find out the peak. That peak will be, of course, be found out. But I'm saying if you want the absolute value, you try to find out that point where this is half, right? That's easy. The density function is in front of you. So equate it to, could equal to half and solve for lambda, right? Not easy, but you can do it. How about if I make one Poisson? Is that easy? Suppose I say f of k given lambda is e raised to minus lambda. So what I gave you is generalization of this. I mean, you can take anything you want. So it's again, I expect this, right? So f of lambda given k. K is the data here, right? Observation. Uh, 3a, because I gave you a problem. This is a simpler case of that problem. So this is f of k given, or p of, because this is discrete given lambda, multiplied by f lambda over f k, right? So this itself, the numerator is given, right? E raised to minus lambda, lambda k over k factorial c e raised to minus c lambda. Now you need to integrate all this, right? E raised to minus lambda, lambda to the power k. So all the e terms are what? E raised to minus 1 plus c multiplied by lambda, lambda to the power k over k factorial. So k factorial goes outside. Lambda goes from 0 to infinity. And as you know, this can be done. This comes out to be some gamma function, right? Where is minus? Here? Yeah. All right, so if you substitute 1 plus c multiplied by lambda to be z, the denominator turns out to be so then this is f of lambda given k is, this is k factorial, right? So k factorial cancels, c cancels. So you have lambda k, c can e raised to minus 1 plus c multiplied by lambda over integral 0 to infinity, lambda is replaced by z over 1 plus c, right? So 1 plus c, so z to the power what? C to the power k, e raised to minus z dc. So this is k plus 1, right? But this whole thing, if I believe this is k factorial, is it? What is it? Right? It is gamma. I think it is gamma k, and maybe k minus 1 factorial, I think. So if I am right, all right, this itself seems to have its own life. I mean, this is something you should be doing, but anyway, let's see. So this is 1 plus c to the power k plus 1, then lambda k e raised to minus 1 plus c. I think it is gamma k, okay. So what? I think this is a gamma distribution, what you are seeing there. Anybody? Hello? You see this as gamma? All right, so that's gamma. Now you should go home and try to find out its mean. You can do it, it's easy, right? You need to do some work in this class. All right, so I did the hard part for you. So I'm saying go home and find out expected value of lambda given k. So that's going to be integral lambda. Then you have to take this density function and multiply and move on, right? Which will be easy because you can make use of the gamma table again. But if you are only interested in map, you don't have to worry about this mess. You can solve from the top, right? Map estimator. Any questions?